So these are the solutions to Physics 211 Homework 13. I've already drawn out problem 1. So part A asks us to find the maximum height that this hoop will go up the ramp. We have all of the conditions that we need to use conservation of energy, right? We have clear before and after pictures. We can account for the work done by all forces, and we don't care about time. So our strategy here is to use conservation of energy. So I can simply write down that the energy in the beginning equals the energy at the end. But that energy comes in two different sorts. The kinetic energy in the beginning, I have both translational and rotational kinetic energy. Now, I'm going to do this problem in a funny way. So I notice that part B asks me to think about a solid ball and whether it would go higher or lower. There's a really easy intuitive way to think about this, but rather than relying only on my intuition, I want to do it mathematically. So I'm going to do something a bit clever. I'm going to write the moment of inertia not as mr squared, but as lambda mr squared. This is a technique you'll often see me do, although I don't think Professor Rudolph typically does it, as a way to think about objects of multiple compositions at once. So I'll note that lambda equals 1 for a hoop, 2/5 for a ball, and so forth. So that way my answer will have a lambda in it, and I can get a final answer that will tell me the answer to part B, and then we'll go back and try to make sense of it intuitively. So what do I have? I have translational kinetic energy in the beginning plus rotational kinetic energy in the beginning, and their sum is equal to the gravitational potential energy at the end. And I can just put in expressions for what all those things are. So that's translational kinetic energy. Rotational kinetic energy is 1/2 I omega squared. And potential energy is mgh. Now, since this rolls without slipping, I know that there is a relationship between omega and v. Actually, before I write that down, I'm going to go ahead and substitute in the moment of inertia. It'll make a little bit more sense if I do that. So then when I put in the moment of inertia, this gives me, and we'll do it on the next line, 1/2 mv naught squared plus 1/2, and the moment of inertia, remember, is lambda mr squared omega naught squared. That equals mgh. Now, since I'm rolling without slipping, I have the no slip condition, which is that the tangential velocity of the side of the ball is equal to its translational velocity, or v equals omega r. Since that's true, I can substitute that in, and I notice that this stuff here, this is just v squared by that. So now let me make that substitution. This becomes 1/2 mv naught squared plus 1/2 lambda mv naught squared. Notice the r squared omega squared turned into v naught squared equals mgh. And now we can do just a little bit of algebra. we can cancel all of the masses. And then that means, with a little bit of solving, this tells us that h equals the square root of, let's see, I can multiply through by 2. So this gives me how shall I do this? No, I just divide by g. I'm being dumb. This gives me 1 plus lambda times, what am I doing? 1 plus lambda v naught squared over g. My apologies for stumbling over that. Notice I'm going to color code this. The 1 here came from the initial kinetic energy, and the lambda came from the initial rotational energy. So this is translational kinetic energy, and the lambda in this numerator comes from the rotational kinetic energy. This is why it's always good to work with variables, right? You can follow the algebraic origin of the things through what you have done. And here, for part B, this answers the question already. No, it would not go as high. Since the solid ball has lambda equals 2/5, less than lambda equals 1 for the hoop. So an intuitive way to think about this is that because it takes less energy to make a ball spin than a hoop spin because its moment of inertia is less, the solid ball in the beginning would start with less energy, which means once all of that kinetic energy is converted into potential energy, there wouldn't be as much of it. So that's problem 1. Let's move on to problem 2. So problem 2 presents us with a loop-the-loop setup of height h. So we have a thing that goes down and then it curls up in a curve of radius r. Let me draw it a little bit closer to the scale that it's drawn in your homework set. And we're imagining a solid sphere. Yes, it's a uniform ball. So this solid sphere starts there and rolls all the way down. And we're asking the minimum height for it to make it around the loop. I want to label a few more things. So here's the bottom. Well, let me redraw the curve. Let's make this a little bit better. Just in terms of art quality here. There's our ground. And finally, here is our curve. So this goes, I don't want a dotted line here. Here is our track. And then bloop. There's the curvy part. So a few more things that I want to label. This height here is h. That's what we're going to be trying to find. The little radius here of the ball is small r, but the radius of this big loop-the-loop is big R. So we want to know, the question is, what height h ensures that the ball makes it to the top of the loop. So here we have to think carefully about why the ball might not make it to the top of the loop. Obviously, if h is large enough, then the ball will have enough energy to reach that height. So the question is not, does the ball have enough kinetic energy to rise again to that height, say if the ramp were flat? The issue is that if the h is not large enough and the ball doesn't go fast enough, it will fall out of the loop. Think again about the frog in the bucket problem that we did so long ago. And folks, I'm very sorry if my microphone level goes up and down. My headset is trying to fall off of my head. So at the top of the loop, let's draw a force diagram and remind ourselves of how this works. So at the top of the loop, our ball here has two forces acting on it. They both point downward. We have its own weight and a normal force, potentially, from the surface above it. Remember, the thing is going to wind up here at the top of the loop. And it's going to be moving at that point with some velocity. We'll label that velocity as v final. And note that v initial is 0. So there's going to be some normal force on it down from the top of the loop. And we'll note that it will fall if that normal force is 0 or less. We did this before. Note that the normal force must be at least as big as 0. If it becomes less than 0, it will fall. So we know that the higher we make the ramp, the faster it will go at the top, and now we have a strategy for figuring out how fast that must be. So if I choose downward to be my positive direction, I know, well, the sum of the forces in the y direction equals MAY. This is at the top of the loop. So in that case, I know that mg, well, plus f sub n equals m omega squared r. Well, actually, we should write it as v squared r, or v squared over r, because v is what we have easiest access to algebraically. We know it's going to fall when the normal force becomes 0. So that gives us a conclusion. You might have remembered this from before. I'm just deriving it again in case anyone has forgotten. That tells us that it falls if v final squared is less than gr. Now, one thing that you might ask is, wait a minute, isn't the center of the ball only moving in a circle of big R minus little r? You might say, wait a minute. This is the path, this thin gray line that I'm drawing, this is actually the path that the center of the ball will move in, and it has a radius of big R minus little r. Yes, that's true. So really, I'm going to write this in parentheses, or vf squared less than g big R minus little r. I don't think many people did this on their homework. And talking to Professor Rudolph, who wrote this question, it's okay if you didn't. We're going to give you full credit if you didn't. Because one of the unspoken assumptions here is that the size of the ball is actually kind of small compared to the radius of the ramp. Um, One of the things about physics and engineering, this is be a little bit of a digression. You can fast forward 60 seconds if you don't care. Um, is that when I was a young physics student, I thought that I would eventually get good enough at math and clever enough to solve anything. And that would be my education, right? I would learn all the laws of nature, and I would learn a whole lot of mathematics, and I would get very clever, and I could solve anything. But it turns out that's not how this works. That real cleverness in physics and engineering, and it's a lot harder actually, is understanding when you can make approximations and understanding the limits of those approximations, um, and when they're valid and when they're not valid. When you can actually ignore air resistance and when you probably shouldn't. So we have made an approximation here by taking little r to be much smaller than big R. In some cases, you might not be able to do that. So in your careers as physics and engineering students or chemistry students or any other technical field, do not be shy about making approximations that simplify your problems and then stating those approximations clearly in your work. That is part of professional practice in the sciences, and it's that skill. We don't teach it like we should. We don't teach the skill of approximation as we should in enough classes. That means it's on you to get good on it on your own. We should teach it more. So don't be shy of thinking carefully about when you can approximate things. Um, so now that I've figured out when it will fall, now I need to figure out what h must be so that it will be going at least that fast. So what must h be for v final squared to be at least as big as gr? Well, here again, we meet the conditions to use conservation of energy. So let's do that. In the beginning, all I have is potential energy, right? So in the beginning, I've got only gravitational potential energy. And that must be equal, well, actually, we're going to do this with work energy. That will make it a little bit easier. We'll do it with potential energy. Sorry, I'm waffling here. So that's the initial gravitational potential energy. I'm just thinking about whether I want to think of gravity as a force that does work or a force associated with potential energy. And in the end, I have three kinds of energy, right? I've got the things gravitational potential energy at the end. I have its rotational kinetic energy, and I have its translational kinetic energy. Because if something is rolling, it's both rotating and translating. So I've got the translational kinetic energy. I've got the rotational kinetic energy. And then finally, I have the final gravitational potential energy. Notice that this height here is 2r, the diameter of the loop there. So just to make super clear what these terms are, this is the initial gravitational potential energy. This is the final gravitational potential energy. This is, not gravitational potential energy, I'm misspeaking. This is the final translational kinetic energy. This is the final rotational kinetic energy. And then finally, this is the final gravitational potential energy. Now, we have the same algebraic pattern that we saw before. I'm going to write the moment of inertia here in a different color and plug it in separately. Going to write it in pink. And I know that for a ball, the moment of inertia is 2/5 mr squared. So let's put that in. It's okay, I'm taking my time doing this because there's an algebraic pattern that's really important for you to see. It's the same one as before, but that's okay. 1/2 mv final squared plus 1/2 times 2/5 mr squared omega squared, and finally plus 2 mgr. Now, this pattern you will need to recognize. I guarantee you'll see this algebraic pattern on the final. There is a pattern here. Notice that you have the combination r squared times omega squared. This is just v final squared by the no slip condition v equals omega r. Yes, it's really plus or minus because it could be going, you could define your coordinate system different ways, but here it's squared, so we don't care. So all of this stuff, right? All of this trash right here, that's just v final squared. So this simplifies. I get mgh equals, so I'm going to have 1/2 plus 1/2 times 2/5. So that's 1/2 plus 1/5. That is 7/10 mv final squared plus 2 mgr. But we know v final squared. We know v final squared is gr. So now we're going to take this. If we want to figure out when it falls, we're going to take that and put it in right here. That gives us, bringing this term on the right over and combining it with the left, that gives us mg times h minus 2r equals 7/10 gr. Oh, actually, I did my algebra in a way I should not have. I shouldn't have brought that over to the left. I'm tired. Supposed to solve for h. So mgh equals 7/10 gr, mgr, plus 2 more mgr. Look, all the m's cancel, all the g's cancel, and we get h equals 27/10 big R. So that may look like a funny fraction, but that's correct. So this is kind of a classic problem, like this problem gets assigned every year, right? And it combines what we did in Unit 2 with objects in circular motion with our new skill of tracking conservation of energy for rotating objects. On to problem 3. So in problem 3, you're asked to think about a rotating stick. It initially starts, well, draw it like so. So there's a stick of length 1 meter, although I'll write it as L here. And it's got a little blob on the left and a big blob on the right. And it rotates. So the big blob goes down, the little blob goes up, and then our final state looks like we have the same stick, but the big blob, weighing more, goes down, and the little blob, weighing less, goes up. Okay, that's nice. We're asked to find the angular velocity of the stick in the final situation. So omega final equals question mark. We know some things. We know that the blob on the left is 2 kilograms, the blob on the right is 4 kilograms, and the overall length of the whole thing is 1 meter. We also know that the mass of the stick is 6 kilograms. Because I am, as always, allergic to numbers, I'm going to use the symbol little m to represent 2 kilograms. So this is m, this is 2m, and this is 3m. So this problem, again, satisfies all of the conditions to use conservation of energy. Note you cannot use conservation of angular momentum here. Angular momentum is only conserved when there aren't any external torques, just like ordinary linear momentum is conserved when there aren't any external forces. But there is an external torque here, right? The external torque is from gravity. The initial angular velocity is 0. The final angular velocity is, something. We're trying to find it. So angular momentum is blatantly not conserved here. So we've got to use energy methods. You also can't do this problem with torque because the angular acceleration is not constant as it swings. So as this thing turns, the torque is going to be different. It's going to pick up factors of sine theta, and the angular acceleration will change. That means that since you're not in constant acceleration, you can't use your kinematics formulas. So energy is, again, our preferred method. Our strategy, again, is conservation of energy. So you can choose your zero height to be any height. I'm actually going to do this problem using the idea of work for gravity. You could do this with gravitational potential energy. It will work fine. I'm going to make the choice to instead think about gravity as a force that does work. So I've got my initial kinetic energy, which is 0 of both types, plus the work done by gravity. We'll color code this a bit. And that's going to be equal to the translational, well, actually we can just think of this as only the rotational kinetic energy at the end. The moment of inertia, though, is going to be tough. So there's no translational kinetic energy. I'll write it down and then cross it off just to make a point. This thing only rotates around its center, and it's not moving at all in the beginning. So we're going to fill in things here in a couple step process. So the work done by gravity, okay, the little ball goes up, so gravity does negative work on it. The big ball goes down, so gravity does positive work on it. So, excuse me. So I've got, and the distance that they move, the distance these things have translated is L over 2. So I've got minus mg L over 2 for the little ball going down, plus 2mg L over 2 for the big ball going up. And then for the final rotational kinetic energy, That is, as always, 1/2 I omega final squared. But now we have to be a little bit clever in thinking about what the moment of inertia is. So let me just label these terms clearly. The little ball goes up, and here the big ball goes down. The moment of inertia here is going to be the moment of inertia of the big one plus the moment of inertia of the small one plus the moment of inertia of the rod. So remember that the moment of inertia of a single point mass is mr squared. And the moment of inertia of a rod about its center, you can look this up in the table, is 1/12 ml squared. Notice that the radius here is L over 2. So this is going to be m times L over 2 squared plus, okay, this, whoops, it's supposed to do the big one first. 2m times L over 2 squared. Small one has a mass of 1m times L over 2 squared. And the rod has a mass of, has a moment of inertia of 1/12 ml squared. So 1/12, not 1/2. I'm tired. So L over 2 quantity squared is L squared over 4. So if I add all these numbers together, so this one is going to give me 1/2 or 2 times 1/4. So that gives me 1/2. This one just gives me 1/4. Whoops, I forgot the mass here. This one has a mass of 3m. Thank you to you people screaming at your computer monitors and telling me I have forgotten that. And 1/12 times m is another 1/4. So this is also 1/4. So 1/2 plus 1/4 plus 1/4 is 1. So the moment of inertia of the whole thing actually winds up being ml squared, but only because we picked those funny numbers, right? Only because the objects were in the ratio 1:3. So this is ml squared. Yes, that's right. I was just thinking over that. So now I know the moment of inertia. Now I can plug those things in to this equation. And this gets me, combining the two terms on the left, this gets me 1/2 mgl equals 1/2 times the moment of inertia, which was just ml squared, although we couldn't have guessed that without adding all those fractions, times omega final squared. Notice that this 1/2 here, the 1/2 in front, for anybody wondering, that came from the L over 2. And conveniently, like literally everything cancels. So let's see, this L cancels that one. This M cancels that one. This 1/2 cancels that one. And I get that omega final is the square root of g over L. Thinking about the units, this makes sense because g has units meters per second squared, L has units meters, so the thing under the square root has units 1 over second squared. Square root has units 1 over seconds, and radians are dimensionless. Now, if we want to put in, so the problem actually told us that the length was 1 meter. So we can actually do this. So this is the square root of 10 meters per second squared divided by 1 meter, which is the square root of 10 radians per second. So this problem may look complicated. You've got all these numbers, but by putting in variables for them, we notice that they all cancel just because they were in that very nice proportion. So thank you to Professor Rudolph for picking the numbers to make the arithmetic easy. Let's move on to number 4. So problem 4, you imagine a child on a merry-go-round. So let me draw this. So we've got a big platform. Boop. We have a child on the edge of it. Over here. And somebody throws a bowling ball or something at him. Always throwing balls at children. And that's going to travel toward him. He's going to catch it, and then after he does, the whole thing is going to start to spin. We told you that you know this angle. You know that angle is theta. And that is r. You know these numbers. I'm going to put them in at the very end. We should calculate the moment of inertia of this whole thing. I'm going to do this up above. I'm going to run out of room if I do it all below. So the total moment of inertia is the moment of inertia of the disk plus the moment of inertia of the child. So the disk is 1/2 mr squared. The child is just mr squared because the child is a small object offset from the center. So our strategy for this problem is a bit different. So in the previous problems, we have used conservation of energy, but that doesn't work here. We do have clear before and after pictures, right? We're trying to figure out how fast the platform will spin after the child hits the ball or catches the ball. So in symbols, we need to find omega final. But we can't use conservation of energy here because we can't account for the work that the child does on the ball when they catch it. This is a collision. So like most collisions, we need to analyze them with conservation of momentum. But in this case, we're dealing with rotating objects, so we're going to be using the conservation of angular momentum. L initial equals L final. Now, in the beginning, this is just the ball. But in the end, and I actually realized I made an error up top, this is the ball plus the child plus the disk. Up top, when I wrote down the moment of inertia, I didn't think about the ball because once the child catches the ball and the ball rotates along with those, the other objects, its mass is also in motion. So, I'm going to need some subscripts here. Again, I am doing this problem for the first time. I've talked to people about it in the physics clinic, but this is the first time I've worked it from scratch. So you're getting to see the process of like how someone approaches a problem and kind of revises what they're thinking. So I'm going to change my notation. Just because I realize I have 3 masses. So the initial angular momentum is just the ball. So I have L ball initial equals the angular momentum in the end. And it's going to be all 3, but the way we represent that they're all co-rotating is by adding up their moments of inertia. So here, the angular momentum of the ball in the beginning is this expression. Well, let me write down. Let me talk for one line just to teach something here. So angular momentum for a small object moving in a straight line you can either think of it as mvr perpendicular or mv perpendicular r or mvr sine theta. Here we know all of those things. We can figure all of those things out. They're all equivalent. I'm going to use this one. Because I've been given that angle. So that means that the mass of the ball times its initial velocity times the radius of the thing times, so this is the angle between the velocity and the radius vector, which I have. It's the right angle, correct angle, not 90 degrees. And then the final moment of inertia is the sum of the disk and the child and the ball. So for the disk, I have 1/2 m disk r squared. For the child, I have m child r squared. And then finally for the ball, I have m ball r squared times omega. So all of this stuff here is the moment of inertia. And this mass on the left, this is the mass of the ball. So omega then is just, and here we just have a giant fraction, it's mvr sine theta divided by 1/2 md r squared. Well, we can at least collect terms, right? mc plus mb all times r squared. So that was pretty simple with symbols. You notice like half of my picture or half of my page is a giant picture. Now I've got to type all these numbers into Google Calculator. So this is the mass of the ball. I should make that clear. So typing these things in, the mass of the ball is lost my Chrome tab where the homework problem is. So the mass of the ball is 3 kilograms times its velocity, which was 12 meters per second. That's pretty fast for a 3 kilogram object. times the sine, or times the radius. So the radius is 5 meters, times the sine of 35 degrees, all divided by this denominator, which is the moment of inertia. So 1/2 times the mass of the disk, which is, oh, we're told it's moment of inertia. I'm sorry. So working back. Yep. All right. So I mistook what we were told. So the moment of inertia of the disk is 150 kilograms meters squared. Working backwards, that means that its mass is 12 kilograms. So if I'm just going to do a sidebar here, I'm sorry about this. This was an oversight in me reading the problem. I thought that we were told its mass rather than its moment of inertia. So I'm just going to do it up on the top of the previous page. So I know that 1/2 m disk r squared is 150 kilograms meters squared. So if I multiply both sides by 150 kilograms, if I divide both sides by, so the radius here is 5 meters, so r squared is going to be 25 meters squared. So if I divide both sides by that and multiply by 2, this gets me that the mass of the disk is going to be 12 kilograms. I am sorry about that. I misread what was given in the problem. It doesn't change the physics, though. I just, in order to get the correct answer so you can check your stuff, I need to type in the right numbers. The mass of the child was 25 kilograms, and the mass of the ball was 3 kilograms, times the radius squared, which was 5 meters squared. And I type all of that into Google Calculator, and I get that omega final is 0.12 radians per second. I really encourage you, when you're using Google Calculator, to type in all of the units. That way, if you mess something up, Google Calculator will let you know. Just as a note, if it tells you something in hertz, that's just something per second, like radians per second. So Google Calculator is telling me right now that the answer is 0.12 hertz. All right, now let's move on to the last problem. One more to go. So this is the Apogee Perigee problem. So we have an orbit. It's not a circular orbit. It's a little bit elliptical, like so. Earth is over here. Not that far. Like there. That's not quite to scale, but it'll make it easier to label things. So we know that the apogee of the satellite, its most distant point, is here. We know that the height above Earth at apogee, again, drawing not to scale, the height at apogee is 2,500 kilometers. The height at perigee is 500 kilometers. The radius of the Earth, which we'll wind up adding to those to figure out the actual distance from the center of the Earth, is 6370 kilometers. And what you know is that this thing is orbiting, and at apogee, it's traveling at 6,260 meters per second. So the apogee is this big number. And this is going to continue to travel around, right? It's going to go here and here and here. And the thing that we want to do in this problem is to find the velocity at perigee, the closest point. So there's a hint in this problem that says you can't use potential energy equals mgh because the force of gravity in space is not mg. Instead, you've got to come up with some other way to do it, or look up the potential formula for potential energy. I'm going to do it both ways. Now, if we can't use potential energy, we need another technique. And that technique here is the conservation of angular momentum, because there are no external torques on the satellite. Now, you might say, wait a minute, what about gravity? But the force of gravity is always directed immediately toward the center of the Earth. And that force doesn't apply a torque, right? Because if we treat the center of the Earth as our pivot, as our point around which things are rotating, then that force doesn't apply a torque because it's directed along the radius. So gravity doesn't apply a torque. So using conservation of momentum, I know that the angular momentum at apogee equals the angular momentum at perigee. Well, note that at both apogee and perigee, the velocity vector is perpendicular to the radius vector, so the angular momentum is just mvr with no trig, right? So at apogee, for instance, that's the radius vector, this little thin gray line that I've just drawn, and that's a right angle. So this problem becomes super easy. Angular momentum at apogee is mv apogee r apogee equals mv perigee r perigee. Now, when we say radius, this is the radius of the Earth plus the height, right? Because I've got to measure to the center of the orbit, or the place I'm considering to be my pivot, which is the center of the Earth. So the masses cancel, right? They've got to. So this means that we'll go ahead and solve and then put stuff in. The velocity at perigee is going to be the velocity at apogee times the ratio of these radii, Ra over Rp, which is Va times the height at apogee plus the radius of the Earth over the height at perigee plus the radius of the Earth. And now we can put all of these things into our handy-dandy Google calculator. Height at apogee is typing into the wrong window. 2,500 kilometers plus the radius of the Earth, which is 6,370 kilometers, all divided by 6,370 kilometers plus 500 kilometers times the velocity at apogee, which is 6,260 meters per second. And this gives me 8,082 meters per second. Very fast, but not out of the ordinary for a satellite. You could also do this problem with the conservation of energy. Let me, you haven't learned what you need for this yet, but some people may do this. Some people may have looked it up, as the hint suggested. So let's also do this another way. So using conservation of energy, I have the kinetic energy at apogee plus the potential energy at apogee equals the kinetic energy at perigee plus the potential energy at perigee. That's pretty easy. But what is the formula for potential energy? It turns out that the general form for gravitational potential energy in space, if you're only thinking about gravity from one object, is minus gmm over r, not r squared. So notice the minus sign out front and the r in the denominator. If you're wondering where this comes from, remember potential energy is just the potential to do work, and work is the integral of force over distance in one dimension. In multiple dimensions, it's this dot product. Well, that's going to be the integral of gmm over r squared dr. R squared is r to the minus 2, and the integral of r to the minus 2 is minus r to the minus 1. So this is gmm over r with a minus sign. So now we can write down what we need. Continuing this down here, we have 1/2 mv apogee squared plus the potential energy at apogee, which is a minus g, big M is the mass of the Earth, m over r, equals the kinetic energy at perigee, 1/2 mvp squared minus r apogee gmm over r perigee. So you'll notice that all of the little m's cancel. Bloop, 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 bloop. And now here is an equation that relates these things. Now at this point you are stymied until you look up big G and the mass of the Earth. You would need those values to complete the problem. We haven't actually given you those things in order to do the calculation, but in fact if you look the numbers up, if Professor Rudolph has chosen his values adroitly, then you'll get the same answer. Let's check that. Why not? So we're solving for the velocity at perigee, remember. So I'm going to multiply everything by 2. This gives us that v perigee squared equals, so I have gm, where big M is the radius of the Earth, over r perigee, minus gm over r apogee. So that kind of looks like a work done by gravity, right? I lost my 1/2 here. Yeah. Yep, it's late. I'm making mistakes. So gm over r perigee minus gm over r apogee. Again, that looks like a work. Plus v apogee squared. Okay, so now we have to type this mess, not a 1/2, a 2. Now we have to type this into Google Calculator. So 2 times the quantity, gravitational constant, times mass of Earth. Yes, you can type those things into Google Calculator. The radius of the Earth we're using for this problem is 6,370 kilometers. Slightly different in different places. No, 6,370 plus the radius at perigee. So over 6,370 kilometers plus 2,500 kilometers minus the gravitational constant. You know what? I have actually goofed. So this is correct, but I've solved for the wrong thing, right? um, we're supposed to solve for the velocity at apogee, so that just gives me the whole thing with a minus sign. Yep, so that's what I meant to type. So I'm typing in all of these symbols into Google Calculator. Gravitational constant times mass of Earth over 6,370 kilometers plus 500 kilometers. Right, so that is, oh, you know what? I'm sorry, folks. The first line was what I wanted to do. I was correct all along. Like, the algebra that I wrote down is right, but like which one solves for the thing that I want to solve for? So, yep. That plus that. Again, you know, I'm working through these problems for the first time right now. So now I'm supposed to add the velocity at apogee squared. So the velocity at apogee is 6,260 meters per second. So now I need to take the square root of what I have here to find the velocity at perigee. And this gives me, hey presto, 8,084 meters per second. What do you know? It's basically the same number up to rounding errors and things. So Professor Rudolph actually looked up real numbers and did the calculation such that it conserves energy. And you can take either approach to this problem. But this is the canonical approach that you're looking at right now to this problem, doing it with angular momentum. You know angular momentum is conserved, but this also conserves energy. So putting conservation of angular momentum and conservation of energy together, you could actually calculate the height at perigee, or the height at apogee, if you knew the other one. Thank you for bearing with me there. I'm sorry for like the, hey, what am I supposed to solve for blooper. It is late and I'm tired. Thank you all for bearing with me through this long solution video. And I will see you all later.